Hello, my name is Trier Mortlock, and I'm a PhD student at the University of California, Irvine. Today I will be presenting our paper HydraFusion, Context-Aware Selective Sensor Fusion for Robust and Efficient Autonomous Vehicle Perception. I'll start by going over some key background to motivate the current challenges in autonomous vehicle perception systems. I'll then introduce our novel framework for sensor fusion, which we call HydraFusion. Then I'll detail the performance our methodology achieves in terms of object detection accuracy and energy. Lastly, I'll summarize the key findings from our paper and open the floor to any questions. This is some brief background on current AV perception systems. On the left, we show a typical AV driving pipeline that progresses from sensing and perception, where sensors are used to collect information from the environment, to planning, where algorithms compute the next objective destination of the vehicle, to control, where the actuation commands to send to the vehicle are determined. Perception systems play a vitally important role in the overall operation of AVs, as the planning and control algorithms heavily depend on what the perception system can tell the AV about its surrounding environment, such as what actors are currently around the AV or where the AV is located locally or globally. On the right is a depiction of the coverage area of cameras, LiDARs, and radars in different colors for an autonomous vehicle. As you can see, there's a lot of overlap in sensor coverage. Motivating methods of sensor fusion and how we can combine the different sensory inputs to maximize the performance of the perception module. In this motivating video from an AV driving competition, we can observe the camera in the top left being obstructed by rain droplets and consequently causing the AV to go off-road and crash into a curb. Despite current methods of sensor fusion, the faulty camera sensor in this example was still able to negatively impact the plan and control of the AV, showing a common challenge in perception and how they can affect the control of AVs. Typical AV perception systems use sensor fusion, as I've stated, across LiDAR, radar, and camera to improve the overall perception. However, existing sensor fusion methods are not robust in difficult driving contests, and they can lack flexibility as they cannot adapt to changing sensing and environmental conditions, which greatly limits their performance. Most existing approaches implement one of two fusion techniques, early fusion or late fusion. Early fusion involves combining data from different sensors before passing the combined data into the machine learning model for processing. While in late fusion, each sensor is processed by a separate machine learning model before fusing the outputs together. Since early fusion processes all of the sensor data together with a single model, it is more efficient, but is highly susceptible to noisy sensor data and sensor failures. Late fusion is more robust to noise because the sensors are processed separately. However, it cannot leverage intermediate features between the sensors, so its maximum performance is limited. To address both of these limitations, we propose HydraFusion, a context and aware selective sensor fusion approach for robust AV perception. Our approach identifies the context from multimodal sensor data and uses it to fuse the best combination of sensors for the current context. By doing this, we can maintain energy efficiency with that of existing methods while dynamically varying both how and when fusion is applied. Now we'll go into methodology. Our methodology operates as follows. First, input sensor data is processed by sensor-specific STEM models to produce an initial set of features. Here, A, B, and Z represent different sensor types. In our approach, STEMs are usually simple CNN layers, convolutional neural networks. Then these features are passed to the gate model, which tries to predict which set of branches are likely to perform best given the current context. It can also optionally use external context, as you see in the figure, to help it make this decision. After selecting the best branches to run, the selected branches are executed. Branches are created for various sensor configurations, as shown in the figure, where a branch can have multiple of the same type of sensor or differing sensor types and quantities. The branch structure contains an object detection backbone, usually followed by a region proposal network, which we'll cover later. The branches overall output bounding boxes and confidence scores for each object the detector detects. We then use our fusion block to fuse these detections and get a more refined set of final detections. The name HydraFusion is inspired by the multi-headed monster in Greek mythology, as our architecture has multiple sensor fusion branches for various sensor configurations. Now we move into the branches. So our branches operate as typical object detectors, taking in sensor inputs and performing both classification and regression to produce object detections. Depending on the branch, early fusion can be implemented where we perform a 2D convolution layer to merge the feature maps of the input before we process them. The structure of our branches can be any typical deep learning object detector. And for our implementation, we use the well-known faster RCNN with the ResNet 18 backbone. The Region Proposal Network, or RPN, is a component within the backbone that implements a sliding window with various sized anchor boxes iterating over the convolutional feature map to generate object proposals. The output of the branches are bounding boxes and confidence scores for each detected object. Now I'll go over how our gating works. So we implemented 3 types of gate models, all with the same goal of ranking which branches would perform best given the current sensor input. First, knowledge gating. Knowledge gating only uses external context, such as the current weather, lighting, and location conditions. We use domain knowledge to specify which branches to choose for each context. The other 2 gating models we used are deep CNN, convolutional neural network-based regression models, where the objective is to estimate the loss of each branch for a given input. Then we take the k lowest loss branches and select those to run. In our work, as we go on later, will show that k = 3 was the most effective for our application. Lastly, the attention gate is the same as the deep gate, but with an added self-attention layer over the CNN features. Next, we move into our fusion block. Our fusion block fuses the multiple predictions from each branch to produce a final set of fused predictions. To illustrate, take the red as ground truth for this car and the 3 blue boxes, A, B, and C, as 3 output predictions. We compare 3 main methods within our work. The first being the common non-maximum suppression, or NMS, in which multiple predictions are sorted based on their intersection over union, or IOU, and their confidence scores. In soft NMS, a function is implemented to not eliminate high overlap boxes, but to reduce their confidence scores. In this example, if B is the highest confidence score, boxes A and C will be filtered out due to their overlap with box B, and their final prediction of NMS would be box B. Lastly, in the weighted box fusion method, the final prediction is generated by computing a weighted sum as a function of the confidence scores for each prediction that are above a certain IOU threshold. In our illustration, each box A, B, and C contributes to the final purple prediction for weighted box fusion based on the confidence scores. Now moving into experimental results. First, I'll detail the dataset we use. So we use the publicly available Radiate dataset to conduct our experiments. Radiate has over 3 hours of annotated driving data with over 200K labeled road actors. Additionally, it records data from 3 different sensors, a camera, a radar, and a LiDAR. We chose Radiate as it's composed of a multitude of diverse driving scenes, as you can see in this image, with adverse sensor conditions. For example, you can clearly see the rain covering the camera image and the effect that snowflakes have on LiDAR measurements. To measure energy efficiency and latency, we used an NVIDIA Drive PX2 with 2 Tegra system on chips. We used TensorRT to compile and optimize each of our models. We'd like to note this is the same hardware platform that Tesla used from 2016 to 2018, roughly, in their autopilot systems for their cars. While performing object detection on the Radiate dataset, we detected cars, vans, trucks, and buses as our vehicles. The most common metric for object detection and AV perception across the industry is mean average precision, or MAP, which balances both the classification accuracy of the prediction and the localization accuracy of the bounding boxes per prediction. For the IOU detection threshold, we use 0.5, which is common in many computer vision applications. In this chart, we plot the map on the y-axis for various fusion methods. The average map of using no fusion for the various sensors was around 65%, with early fusion and late fusion both improving results. HydraFusion, with 3 different late fusion strategies shown in gold here, is shown to be the most robust across the entire validation data set and can achieve over 13% improvements across traditional sensor fusion approaches. Next, we evaluate the effect of different gating methods and the number of branches selected. As shown, k=3 achieves consistently high performance compared to the other variations. You can also observe that with large values of k, object detection performance can also decrease, motivating our selective sensor fusion approach. We found that the best performing combination was k=3 with attention-based gating. However, we do note that future research directions should include studying an adaptive value of k. To demonstrate the practicality of HydraFusion for real-world deployment, we analyzed the energy and latency performance on the NVIDIA Drive PX2. We found that HydraFusion uses less energy than late fusion while improving the performance by up to 15%. Likewise, we found similar trends in latency as HydraFusion outperformed late fusion. Ultimately, our findings support that HydraFusion can be reasonably deployed in current applications where methods of late fusion are being used. To further contribute to the research community, we have open sourced our code available at the following link. To summarize our work, we presented an adaptive sensor fusion framework that can be applied to a variety of sensor fusion problems. We proposed different gating strategies where we showed the benefit of learning the context of a driving scene over knowledge or rule-based gating. And we also showed that methods using attention can outperform other deep learning approaches. We showed efficient execution on hardware, justifying that HydraFusion can be deployed in current AV setups. And lastly, we showed robust object detection performance in a number of challenging driving scenarios. We'd like to thank our sponsors at the National Science Foundation for funding this research. I thank you all for listening and look forward to answering any questions that you may have.